Welcome to this lecture of hyperbolic geometry. In this lecture, we'll find the geodesics of upper half plane with respect to hyperbolic metric. In order to find the geodesics of this upper half plane, we need the fact that Mobius transformations are conformal, meaning that it preserves angles. So let us begin. In order to prove Mobius transformations are conformal, we'll prove a more general thing that analytic functions are conformal. First, let us define what do you mean by analytic function. So let us take an open set. So let U be an open set in C. C means the set of complex numbers. So a function f from U to C, so f is a complex valued function, is said to be analytic on U if f is continuously differentiable on U. So what is the meaning of continuously differentiable on U? So that is, so this f prime A, so this limit, so f prime A is nothing but this limit fa plus h minus fa divided by h exists for all A belonging to U, and this derivative of f prime, derivative of f is continuous. So f prime is continuous on A. So I'm sure that you have learned this definition of analytic function in complex analysis. And now let me define what you mean by conformal map. So let us take two differentiable paths. So let gamma 1, gamma 2 be two differentiable paths, be two differentiable paths in C. That is, so what is the meaning of differentiable path? So this limit, so limit t naught tends to 0, gamma I t plus t naught minus gamma t naught divided by t exists for all t belonging to this open interval AB, and for I equals to 1 to 2. So whenever this limit exists, so we denote it by, so this is my notation. So denote it by gamma I prime t naught. So now, so first let me define, so what do you mean by angle between gamma 1 and gamma 2 at some point z naught belonging to U. Okay, so what I am assuming here, so this gamma 1 and gamma 2, so they intersect at this point z naught. So these are my two paths, gamma 1 and gamma 2. And also let us assume, so there exist points t1, t2 in this open interval such that gamma 1 t1 is equal to gamma 2 t2 is equal to your z naught. So the angle between, so this gamma 1 and gamma 2 at z naught, so it is the, so following thing. So you take argument of this gamma 2 prime t2, gamma 2 prime t2, so this will be a complex number. So you take the argument of this thing minus argument of this gamma 1 prime t1. So this is the definition of angle. And a map f from U to C is said to be conformal So if this argument of this gamma 2 prime T2 minus argument of gamma 1 prime T1 is equal to argument of this, you take F compose gamma 2 prime T2 minus argument of this F compose gamma 1 prime T1. So F is said to be conformal if it preserves the angle. And this is true for, so if this holds for all paths, for all differentiable paths, gamma 1 and gamma 2 on U. So whenever we have, so let me draw this diagram. So whenever we have these two paths, so Z0 belongs to U. So gamma 1 and gamma 2, so then intersect at the point Z0. And you apply F on this thing. So you'll get the path F compose gamma 1 and F compose gamma 2. So gamma 1 prime means, so this will give you the tangent vector here. So this will give you the tangent vector of this gamma 2. You take this angle. So this F, so this will preserve this angle. So if this happens, we call this F to be a conformal map. So next observation is, if I take F to be analytic, so then F is conformal. So let me write this proposition. So analytic maps are conformal. So what is the proof of this? So let F be an analytic function. And so again, we have this diagram as above. So let us take two paths, gamma 1 and gamma 2, intersecting at the points at naught. So we want to prove this equation here. This equation here. So F is given to be analytic function. So what we have here now, so F compose gamma I prime T. So this is equal to your F prime of gamma I T times gamma I prime T, where this I is equal to 1, 2. So this is the product of these two complex numbers. So therefore, so the argument of this F compose gamma I prime T is equal to your argument of this F prime gamma I T plus argument of this gamma I prime T. Now it is given that this Z0 is equal to your gamma I T I, where this I is equal to 1, 2. So therefore this F prime gamma 1 T1 is same as F prime gamma 2 T2. So which is nothing but equal to your F prime Z0. So this implies that these two complex numbers are same. So therefore the argument of this F prime gamma 1 T1 is same as the argument of this F prime gamma 2 T2. So therefore I equals to 1 and 2, so you'll get two equations. So from the star, so what you'll get, so argument of this F compose gamma 2 prime T minus argument of F compose gamma 1 prime T is equal to your argument of gamma 2 prime T minus argument of gamma 1 prime T. So this proves that So this F is conformal. So therefore, so in particular, so Mobius transformations are conformal maps. As they are analytic functions. So now we are in the position to find the geodesics of this upper half plane with respect to this hyperbolic metric. So geodesics of this upper half plane. And let us recall, so what is the metric, hyperbolic metric on this upper half plane? So we have taken the square of this line element to be dx square plus dy square by y square. So this we have called to be the hyperbolic metric on this upper half plane. Okay, so first let me define, so what do you mean by geodesics? So let us take 2 points. So let ZW belongs to H2. A piecewise differentiable path gamma between Z and W in H2 is said to be a geodesic. So if the length of gamma, so this is equal to the distance between these 2 points, Z and W. So dH2, it is the hyperbolic distance. It is the hyperbolic distance between Z and W. So gamma is a path. If it realizes the distance, so then we call this gamma to be a geodesic. Okay, so theorem. So the geodesics in upper half plane are semicircles and straight lines orthogonal to the real axis. Okay, so let me draw this picture here. So this is my real line, and if I take any vertical line, so straight line orthogonal to this real axis means all these vertical lines. So this vertical line, so this will be a geodesic. And now if I take a semicircle whose center lie on the real axis, so then that will be also a geodesic. Because this semicircle, it is orthogonal to real axis. So these are my geodesics. So now let us prove this theorem. So let us take 2 points. ZW belongs to your upper half plane. So first let Z to be equal to your IA and W to be equal to your IB, where this A is less than your B. So let gamma be a differentiable path joining this 2 points, Z and W. So differentiable path such that gamma of 0 is equal to IA, gamma of 1 is equal to your IB. And let us also write, so this gamma t, so this is to be your xt plus iyt, where this t is varying in this closed interval 0, 1. So the length of gamma, so this by definition, this is the following integration, 0 to 1 root over dx dt square plus dy dt square divided by yt dt. So now note that, so the numerator of this integrand, it is always greater than equals to mod of dy by dt. So therefore, so this integration 0 to 1, so this integration is always greater than equals to this integration 0 to 1 mod dy by dt dt by dt. And this is again, so this integration is again, because it is positive mod I have taken, so this integration is again, it is greater than equals to dy by dt divided by yt dt. And this is basically equal to this integration a to b dy by y, so which is nothing but equal to your log of b by a. So what we have proved that, so length of gamma is greater than equal to log b by a. Now let us take, so let beta t, so this to be equal to your I times a plus t times b minus a. So t is again varying in this closed interval 0, 1. So beta t, so image of beta, it is a straight line joining this IA and IB. So I'm just taking the convex combination of this IA and IB. So beta prime t, so this is equal to your b minus a times I. So mod of this beta prime t, so this is equal to your b minus a. So now if I compute the length of beta, so this will be this integration 0 to 1 mod of this b prime t divided by the imaginary part of this, so a plus tb minus a dt. So this will be equal to your log of b by a. So this you can check. So therefore, so what we have proved that, so thus, so length of gamma is always greater than equal to length of beta. And this is true for all piecewise differentiable path gamma with gamma 0 IA and gamma 1 to be your IB. So therefore, so this will imply that length of beta, so this is equal to the distance between IA and hyperbolic distance between IA and IB. So this implies that, so beta is a geodesic between IA and IB. So therefore, what we have proved that, so if I take this vertical line, so this imaginary axis, so this is my imaginary axis, in upper half plane. So this is a geodesic. Okay, so now how to find the other geodesics? Okay, so now let us take an isometry. So let us take T to be an isometry of this upper half plane. So T is an isometry, so T preserves the distance. So therefore, if I take a geodesic, let us take beta to be a geodesic. Suppose beta is a geodesic in H2. So this will imply T of beta is a geodesic in this upper half plane. Okay. So now, if I take T to be a Mobius transformation, so this will imply T is conformal. So I have taken this beta to be this imaginary axis. So this is my beta. So this we have proved to be geodesic. So T of beta is also a geodesic. And now if I take T to be a Mobius transformation, so T of beta, it will be either a straight line or it is a part of a circle. So this thing we have proved in the last class. So let us take T to be an element of this PSL to R. So let us take Tz to be your Az plus B by Cz plus D, where this A, B, C, D are my real numbers. And so this AD minus BC, so this is equal to your 1 because we are taking this ABCD in this SL to R. So if I take this thing, so T naturally, it is an isometry of this upper half plane. So this also we have proved. So T is also a Mobius transformation. So T of beta, so this will be, so T of beta, so this is either a straight line or a part of a circle. So this T of beta, because T is conformal, so this angle will be preserved. So T of beta, if it is a straight line, it cannot be like this because so this angle will not be preserved. So this 90-degree has to be preserved. So if T of beta, if it is a straight line, it has to be vertical. So this is one possibility. And T of beta, it is a part of circle. So again, so it cannot be something like this because so this orthogonality has to be preserved. So here it is not orthogonal. So this possibility will be not there. So the circle will be of this form only. So circle will be orthogonal to the part of the circle. So it will be orthogonal to this real axis, and which is nothing but the semicircle. So beta is orthogonal to real axis. And also note that and T of R is equal to R. So this will imply that T of beta, so this is orthogonal to R. T of beta also it lies because T preserves the upper half plane. So it is certainly T of beta is contained this in this upper half plane. So this implies that T of beta is either a vertical line or a semicircle with center on real axis. Okay, so what we have proved that, so if I take any vertical line and semicircle, so these are my geodesics. But so are there any other geodesics? Okay, so this will prove that so there does not exist any other geodesic. So suppose I take these 2 points. So let Z1, Z2 belongs to this upper plane. So suppose Z1, Z2 does not lie on a vertical line. So then, claim is that, so there exists a semicircle orthogonal to real axis and passing through Z1 and Z2. So how to prove this thing? So you take this real axis first and take these 2 points, Z1 and Z2. So just draw a line segment joining the Z1 and Z2. Take the perpendicular bisector. Take the perpendicular bisector. So this will meet the real axis at some point. Call it to be X. So now what to do? So this to so you take this 2 straight lines join. So join Z1 to X by straight line, Z2 to X by straight line. So this 2 lengths, so this will be same. So distance, so the Euclidean distance between X and Z1 will be same as the Euclidean distance between X and Z2. And now you draw a semicircle with center X and radius distance between X and Z1. Yeah. So this proves the claim. So this proves the claim. Okay. So if Z1, Z2 lie on a vertical line, so then we have to do nothing. So if they doesn't lie on the vertical line, so then what we have shown that there exists a semicircle which passes through Z1 and Z2. Okay. And so now why there does not exist any other geodesic? So suppose if I take 2 points Z1 and Z2, first let us take these 2 points on the vertical line. So if I take any other path like this, call it to be gamma. So we already proved this thing. Suppose beta is the vertical line, vertical geodesic joining this Z1 and Z2. And if I take any path gamma, differentiable path gamma joining Z1 and Z2, so then already we have proved this thing. So length of gamma will be greater than or equal to your length of beta. So if gamma is not a vertical line, so this in fact, so length of gamma, it will be strictly greater than length of beta. So if gamma is not a vertical line. So this will prove that so beta is the only geodesic joining the Z1 and Z2. And now suppose the Z1 and Z2 does not lie in a vertical line. So then there exists a semicircle with center on real axis. And again, using the same argument, you can prove that. So if I take any differentiable path or piecewise differentiable path joining Z1 and Z2, if image of this gamma is not equal to your or does not lie on beta, so then here also, so length of gamma, it will be strictly greater than length of beta. So this will prove that, so this semicircles orthogonal to real axis R and vertical lines are the only geodesics of this upper half plane. Okay, so we'll stop here.